let's say that we have a shell of mass. So it's a sphere, but only the area. There's no mass inside of the sphere. It's only on the surface. So it's a shell of mass, and we have density sigma. It's uniform density everywhere, and we have a radius, let's say A, for this sphere. And we have our object of mass little m here. So it's a point object, and it's at a distance from the center there that is capital R. And so we want to find the gravitational force. And so we are going to integrate over the entire surface. So every little bit of this surface, little tiny areas, produce a gravitational force that we need to add up. So we have an infinitesimal contribution from every piece, right? We have minus g times that mass of this point object times, let's call, this could be a dm. Well, it turns out we'll want to use symmetry here, but we have little pieces of this. Let's call them dm. And there will be a direction, right, associated along the line between this and that piece of mass, that little area of mass, and we divide by the distance from there, which is r. So let's find a convenient way to do this calculation. So here is, make this a little bit larger, and we have some symmetry here, so we can kind of divide this up into little rings of matter. So it's something like a little ring of matter with some extension here. Something like that. So here is the center of the sphere, say, and we're going all the way up to, that object is over here. We have a piece of this little ring here, and it's at a distance from there. We can call that distance r. There's some angle here. There is, from here to there, that's the radius A. We have an angle here, right? This angle is changing as we consider different rings. We have, let's maybe use a different color. We have, if this is R, then this little ring has radius. Let's indicate it there. It's A sine of theta. And the width of this, so the width of this would be A d theta. And so we're going to parameterize this in this way. Let's say that this is the z direction. Right? We're going to get a gravitational force which is in the z direction, and then this is the xy plane. So how much matter is in here? And we're going to then add these little rings up to get a net force. All right, so we have a minus g little m, and the amount of matter there has to do with this region, which is, right, so we have a 2 pi a sine theta. So what is this region? And then we have a distance, an infinitesimal distance there. So we end up with 2 pi a sine theta a d theta, so we get an a squared d theta, and then we have to multiply by the density to get the amount of mass there. So we have the sigma here, and so that's the infinitesimal amount of mass in this little ring. Okay. We're going to divide, now these things are not separate, but let's just write, we're dividing by the distance that we have here. There's a distance r squared, but let's notice that a little piece over here produces a force which is along this line, and this little piece produces a force which is along that line, and so the horizontal components cancel out, and therefore we can recognize that we are only going to get a net vertical component. So we have a cosine of phi here, and we have to figure out what this quantity is. These are not independent quantities. Cosine phi, and then we have a k hat, because we're going to end up in the z direction. Okay, so that's the infinitesimal force produced by this little ring, and we're going to integrate these little rings as they go smaller here, and then they become larger, and then they become smaller again. And so the angle theta is going from 0 all the way to opening up to here, to pi. And so we'll continue this calculation in the next lecture.